Hello and welcome to Math 250, section 6.1. Today we'll be talking about the geometry of vectors. We've spoken a lot about vectors in this course. As a refresher, a vector is a directed line segment that has both magnitude and direction. In our course so far, we treated vectors as this one column matrix, so to speak, with two, maybe three rows. But in today's class, we'll look at all the different properties that vectors have. First, there's this concept of length, and it's very, very similar to Pythagorean theorem. If we want to find the length of a vector, we square the u1 component, add to it the square of u2, then take the square root if we're in R2. If we're in R3, we repeat the process, but also with the u3. So we square u1, square u2, square u3, add them up, then take the square root. And this repeats for R4, R5, etc. If we want to talk about distance between vectors in Rn, this is best represented geometrically. So say I have two vectors u and v. If I want to find the distance between them, you're sort of going tip to tip. You want to figure out how far apart are the tips of the two. And to visualize it, you draw a vector outside of the two vectors that runs parallel to the actual distance. And that kind of shows it to you that we're really just, finding the difference between vectors u and v by finding the norm. We subtract the components of u and the components of v, and then we do that distance calculation I was referencing earlier with squaring and adding and then taking the square root. But it makes a nice little picture here. So if I want to find the distance between vectors u and v, I can simply draw a directed line segment at the vertex of the intersection straight out to the tip of u, and then that vector u minus v, I can find the distance of that, and that will give me the distance between the two vectors over here. Here's a way to understand Pythagorean theorem using vectors. So in high school, you learned Pythagorean theorem as a squared plus b squared equals c squared, assuming we had a right triangle. We can apply similar logic to vectors. If I have a vector u and a vector v that meet at a 90-degree angle, then if I would like to find the distance between those two vectors, again, we can mimic the same argument. If I go to the vertex of the angle formed by the two vectors and draw out a vector that runs parallel to the actual distance between the two, that would give me the length, the distance between the two vectors. And this gives us a pretty powerful statement. Two vectors are perpendicular if and only if we find these distances and square them and then add them up, that it also equals, what we know from high school as the hypotenuse squared. It also equals v minus u, their norm, squared. So just to prove it a little bit, this comes from the fact that if we are finding the norm, we're just squaring the components inside. So let's assume, just for, since we're in a flat space here, we're going to assume that we're in R2. If I would like to prove that this statement does hold up, I can re-understand this as v1 minus u1 squared plus v2 minus u2 squared. In other words, I have these two vectors, v and u, each with two components. And if I'm finding the norm, again, I'm doing like a Pythagorean theorem type calculation. So I'm just finding the difference of the first components and the difference of the second components, and then I'm squaring those differences and adding them up. For this one, again, just dealing with u, if I'd like to find the norm of u, that is just each of the individual components squared. And then same thing here. If I'm dealing with vector v, which has components v1 and v2, that would just be the square of each of the components. If you've never seen norm before, I realize I mentioned it a couple times. I'm assuming you've seen it in a class before, but the norm of a vector v simply means that we take the individual components, v1, v2, all the way out as far as you need to go. So I'll just call that vn. And you square those together and take the square root. Since we're proving a statement, I'm not going to use the square root right now, but that's where these squared terms come from. Using polynomial distribution rules from algebra, we can expand each of these out to v1 squared minus 2u1 v1 plus u1 squared. Thank God for the undo button. And then if I square the second group out, that's v2 squared minus 2u2 v2 plus u2 squared. And I'll leave the right side alone because there is nothing there to add together, no like terms. And what you'll notice is if we look at both sides, I have a v sub 1 squared on both sides that I can subtract off of each side. I have a u sub 1 squared that I can subtract off of each side. If I look at the v sub 2 squared, I also have 1 on each side. And then same for u sub 2 squared. I have 1 on each side there as well. So now I'm in a position where I have negative 2 u1 v1 minus 2 u2 v2 equals 0. I can then divide everything by negative 2 just to get rid of some of these excess numbers. And I arrive at this statement right here. And this is really, really, really important. Perhaps some of you have seen this before. This is called the dot product. And the dot product just means that if we take two vectors, u and v, so I'll have my components u1 and u2, and v1 and v2. Dot product just means that I multiply the first components together and the second components together. If I add them up and I get out 0, that means that the vectors are perpendicular. So that's something that comes out of using the Pythagorean theorem in vector language. We can formalize it here by calling the dot product u dot v, and again, these are vectors, that's why they're bolded. And then we have u1 v1 plus u2 v2. If I go out to r3, which I'll do in my next example, I would have u3 v3. We can go all the way out to un vn. But we say that u and v are orthogonal or perpendicular if the dot product of u and v is 0. In linear algebra, we don't really use the phrase perpendicular. Instead, we call them orthogonal. And if you break the word apart, ortho means right, like orthodontist, you want to get your teeth right. And then gon means angle, so right angle. We're going to try a sample problem with two vectors in R3, vectors u and v. I graph them on the 3D axis in case you haven't taken multi yet, or you've never seen a 3D plane before. We have our x-axis over here that goes this way, just like this. I don't want to blend the colors up too much, but the x-axis is over here. We have our y-axis going this way. So it's sort of like laying a piece of graph paper flat on the ground. And then the z-axis is the one that you see vertical. This one right here. So we can graph 3D vectors in very much the same way we graph 2D vectors. We see how much right or left to go, and then up or down on the y-axis, and then we go up into the third dimension. And I've graphed these two for you. The vector u is the one that you see in blue, and the vector v is the one that you see in red. We're going to find a couple of things for each vector. So part A says, what is the norm of each vector? And norm is just a fancy word for length. So if I would like to find the norm of vector u, I simply square each of the components, add them up, and then take the square root. So I would do 2 squared plus negative 1 squared plus 3 squared. So that's 4 plus 1 plus 9 and that gives me a norm of radical 14. Very similarly for v, if I want to find the norm of v, I also square each component and then add them all together. So I have 0 squared plus 4 squared plus 2 squared, 0, 16, and 4. That makes radical 20. If you'd like to simplify it, by all means, it is 2 radical 5. But that would be the norm of each vector. Hopefully that makes sense. For distance, we spoke about distance on the previous slides using Pythagorean theorem. So we could do that as that should just be one line. U minus v, we can find the norm of u minus v. So to do that, simply subtract component by component. 2 minus 0, that's a 2. Negative 1 minus 4, that would be negative 5. And then 3 minus 2, that would be 1. So we're just subtracting them component by component, square each of those differences, and then we can add them together. So I have 4, 25, and 1. So that would give me radical 30 as the distance between the two vectors. So that would be, graphically speaking in the plane, tip to tip, how far apart are these two vectors? We got radical 30 for that. All right, part C, the dot product. So that, like we said before, was just multiplying component by component and then adding up the results. So I would do 2 times 0. So that would be u1 times v1. And then negative 1 times 4, that would be u2 times v2. And last, I would have 3 times 2, that's u3 times v3. So my total would be 0 minus 4 plus 6, and my dot product would equal 2. Based on the picture, it doesn't seem like these vectors would form a right angle, so we think that they would not be orthogonal, but the dot product gives us the answer more directly. So because the dot product is 2, the answer is no. And the reason for it is that the dot product is not 0. So we can just write u times v, with the dot product is not 0. So these vectors will not meet at a right angle. And the process I just used here, I chose R3, but it applies also to R2, R4, regardless of how many components you have in the vector, you just might have a little bit more arithmetic with more components, but this type of procedure works no matter what. So now that we've worked with norm a little bit, and also the dot product, we'd like to look at some additional properties of vectors in the dot product. I've copied some text out of your book here because I think it's really important. One useful consequence of identifying a dot product as a matrix product is that it enables us to move a matrix from one side of a dot product to the other. More precisely, if A is an m by n matrix, U is an Rn, and V is an Rm, then we are able to move a matrix A through the dot product like this, and even use its transpose. Again, the dot product gives you a scalar as an answer, so that's why we're allowed to do this. And if you'd like a proof of it, we can more formally show it by starting with the left side, transposing AU. Remember, when we transpose things, the order switches, so that turns into U transpose A transpose. We can apply associative property from chapter 1 to regroup the parentheses. And then, transposing a vector doesn't really do a whole lot. So that gives us back out U as a vector times A transpose times V. There are a variety of other properties here in Theorem 6.1 that we'll work out on the next step. And we've already kind of touched on them. So if I'm finding the norm of a vector U, that's equivalent to, like we showed before, square rooting and adding up each of the components squared. But if I'm finding the norm squared, the square roots go away. So I'm really just multiplying u by u. In other words, finding the dot product component by component. If the dot product of the two vectors is 0, if and only if one of the vectors is 0. So the only way to get out a 0 answer as a scalar is if one of the two vectors itself is 0. For the dot product, the order doesn't matter, so it's commutative. You can multiply vector u by vector v or v by u and get the same result out. D and E look like distributive property. For the dot product, if I have u times v plus w, I can multiply u on the left, or if u is on the right, I can also multiply that on the right for each term. If vector u is multiplied by a scalar, we have movement that we can allow. We can regroup it using associative property as c times the dot product of u and v, or u with the dot product of c times v. And then if I'm finding the norm of a scalar times u, simply take the absolute value of the scalar and multiply it by the norm of u. I like to do a problem where we actually use these properties so you can get a feel for what they look like. The first one's pretty quick. The second one's a little bit more involved, but it uses many of the properties in Theorem 6.1. I have pasted it here for convenience so that as we go through it, we can refer back and understand why the answers are what they are. So let's say that we have three vectors, u, v, and w. We know that, and we don't know the individual components, but we know that the norm of u is 3, the norm of v is 4, the norm of w is 2, the dot product of u and v is -2, the dot product of u and w is 5, and the dot product of v and w is -3. First, we'd like to compute 2u plus 3v and its dot product with w. So the fact that we have the vector on the right, that means we want to take a look at Theorem 1.1 part E. We can basically distribute by w on the right. So this would be the same thing as 2uw plus 3vw. And that's enough information for us to go ahead and solve the problem, because we were told that the dot product of u and w is 5, and the dot product of v and w is -3. So we can just plug those right in, and we get out 10 minus 9, which equals 1. Very straightforward. The second one, however, is a bit of a beast. We want to compute the norm of u minus v plus 3w squared. So a little bit more work now that we have 3 characters and also that we're squaring it. So the first thing we're going to do is apply property A. If I'm finding the norm of something squared, that's equivalent to multiplying the inside by itself. So this equals u minus v plus 3w times u minus v plus 3w. And I'm just going to note the property that we used here. And then the last problem too, I'll just go ahead and put that up there, that we use property E for that. So that's the first part. And I think you guys all know by now, when you're squaring something, you're multiplying it by itself. Next, we'd like to try to multiply this out. So we're going to use property D, the left side distributing, and distribute each of the terms on the left to each of the terms on the right. So for my next step, I'm going to do vector u multiplied by u minus v plus 3w. Then I will do vector v. Oh, that appears to be negative, so let's just switch that. Vector v. So I'll then do this one across all 3. Vector v gets multiplied by u minus v plus 3w. And then the last one, I'll do 3w to each of the terms on the right. And again, this was by property E. All right. Sorry, that was property D. I apologize. Wrong letter. That was property D. Okay. So next we will multiply these together. We want to like push each of these guys out. So I have U by U would be first. When I go here, and then I have U by V, and then I have U by 3W. So that's my first group. Then I have minus V by U when I start to distribute the V. And then I'm going to have plus, because I'm doing a negative to negative, V by V. And then minus V by 3W. So I'll just put that all in one group there. And then the last part, I want to distribute the 3W out. So that is 3W by U. And then I have 3W by negative V. And then I have 3W by 3W. Lots going on there. So that was the actual distributing, out of what we need. And now comes, some of the more cumbersome parts. We just want to regroup things with our scalars and with the correct order, because we're basically in alphabetical order. We have UV, UW, VW. So in places where we don't have that, we want to just make sure that we do have it. Like here, I have V by 3W. So I can rewrite that as 3VW. Just push the 3 out to the front by using property F, that we can take those scalars out and move them. Same thing with the next one. This would be property C. I have V by U. But up here, they gave me the dot product of U and V. So let me just rewrite it in that order so that we stick to what we have. The next one is V by V, so that just stays the same. My U's and V's all look the same. And then for the next one, I have negative V by 3W. So again, I could use property F on that with the scalar. So I could just bring that out to just be negative 3VW. This should be a U. Maybe I'll make these U's a little different. They're all starting to look similar. And then for the last group, I have 3WU, but remember alphabetical order, so I will just switch that around using property C. 3WV, but we have VW, so I'm going to write that as 3VW. And then the last one is 3W by W. Just fit that in. Okay. Lots of stuff going on here. We also, believe it or not, have like terms and things like that as well. So I'm gonna combine two steps here. I'm gonna combine like terms and also rewrite a couple of things in the interest of time and space. So this U with U by property A, that is the norm of U squared. So I'm just gonna write that out like that. With UV, I have a negative UV here. I'm just going to underline it, and then I have another one over here. So I'm going to just combine those together as a minus 2 UV by adding up like terms. I also have a V by V product, so that by property A is going to be the norm of V squared. More like terms, so I have a dot product of 3 UW, and then I also have that over here. I'll underline those in yellow. So I have one here and one here. So that is 6 UW. Lots of colors going on here. And then I also have another group of like terms. I have 3 VW here and negative 3 VW here and negative 3 VW here. So that's going to be negative 6 VW. So that takes care of that. And then I think the only thing left that I didn't touch was the 3 VW by 3 VW. I think I left out a 3. So this should be, so this last term is 3W by 3W. So that's actually 9W by W. So that makes a 9 norm of W squared. I apologize for missing the 3. All right, and then now, out of breath. So now the final step, we want to just replace our values that we were given. The norm of U is equal to 3. The dot product of U and V is negative 2. The norm of V is equal to 4. The dot product of U and W is 5. The dot product of V and W is negative 3. And then the norm of W squared is 2 squared. So I can replace that there. And then if you add these all up, you should get a grand total of 113. So that was by far much more work than the first problem, but we used almost everything in this list. We except for maybe part B with the dot product being 0, that didn't quite happen. We used almost every other property in this list. So I thought this would be a good way to exercise some of these key ideas about the dot product. For the next part of our lesson, we're going to take a look at an important concept called orthogonal projection of a vector on a line. I'm going to explain where the following formula comes from by using an image from the book as well as a short proof. This is something that's going to carry us through not only 6.1, but the remaining sections in Chapter 6. So suppose that we want to find the distance from a point P to the line L, and that's provided to you up front, as given in the figure shown here. It is clear that if we can determine the vector W, which means, somewhere along the line, on the line, then the desired distance is given by the norm of U minus W. So that goes back to our discussion earlier where we draw that line at the vertex out parallel to the actual distance tip to tip. The vector W is called the orthogonal projection of U onto L. To find vector W in terms of U and L, we let V be any non-zero vector along L and let Z equal vector U minus vector W, just as we have shown here in the picture. Then we say that vector W is equal to C times vector V for some scalar C. So that just means that, since they both lie along the same line, one is a scalar multiple of the other. They both have the same direction, but one might just go a little bit further than the other. Since we've set this up in such a way that Z and V are orthogonal, meaning they mean at a right angle, because we dropped, that perpendicular along the way. So I have vector Z meeting vector V over here at a right angle. That means that their dot product is 0. So we start the proof with that. We'll start with the answer 0. That equals the dot product of Z and V because they are orthogonal. We also stated up front that Z was the difference of vectors U and W. That was our drawing right here. Using substitution, we also said that W was equal to vector V times a scalar C. So that then gets substituted out in the next step. So lots of stuff going on. From this step to this step, notice we use our previous theorem where we distribute the W backwards. So I have the V backwards. So I have the dot product of U and V, and then the dot product of V and V multiplied by C. Again, using the previous theorem, the dot product of a vector with itself is just the norm squared, so we replace it with that. So at this point, we reached a place where we started with 0 and we ended with a dot product minus a scalar times a norm squared. And if we solve this for C, we get C equals the dot product of U and V over the norm of V squared. And that would just come from moving this term over to the other side. In either order, you can move the dot product over too and then divide. Doesn't matter. But to solve for C, then just divide out on both sides. So it's really up to you how you want to do it. So that's what C is. So then when I write out my vector W, which is the vector of interest, that's the one that'll, that we can draw our perpendicular from the tip of vector U. If I go back to W equals C times V, W equals vector U by vector V, the dot product, over the norm of V squared times V. So I can sub that right back in for where C was. So therefore, the distance from P to line L is given by, instead of vector U minus vector W, we can write it out as this difference here in terms of vectors U and V. And like I said, you're going to see this over and over and over again throughout the next couple of lessons. I know there's a lot of letters here. It's a bit of letter overload, so feel free to rewind and watch it again. Try to understand why each step is allowed through this unraveling, and we will next use it in an application problem. Compute the orthogonal projection of vector W. Compute the orthogonal projection W of vector U on L, and use it to compute the distance D from the endpoint of vector U to line L. So for this problem, we are going to work this out numerically and determine the orthogonal projection as well as the distance. In order to do a problem like this, we definitely want to start with our vector U, 3, 5, but we will also need a vector V. And vector V, as you'll recall from our previous slide, that is just a vector along the line. So if I go to my given line and I notice that it's y equals 4x, so I have a little bit of freedom here to choose a point that fits on that line and write it in vector form. So to keep things simple, I will use 1, 4 as my my vector V. Over here in the graph, I just graphed y equals 4x in red. And then I also graphed the vector 3, 5. If you're thinking of it in like a tip-to-tip format, what we're trying to find is the orthogonal projection of the blue onto the red. So that's our goal here. What kind of segment can I draw from the blue onto the red that hits at a right angle? So that's what we'll be working at here. All right, so the first thing we do is we want to use what we found on our previous discussion. We want to find the dot product of U and V over the norm of V squared times vector V. That will help us find our projection and our distance. So to plug this all in, I'll work this out. So V by U, that dot product would be 3 times 1 plus 5 times 4. That is our numerator. Our denominator, the norm of V, so the norm of V is 1 squared plus 4 squared, but then we want to square that. That's what the norm of V squared is, so technically you don't even need the square root and the square, it just cancels one another out. And then I recopy vector V after it like this. So I would get out 1, 4. If I clean this up with numbers, then I get out 3 plus 20, which is 23. And then on the bottom, I get 1 plus 16, that's 17. And like I said, the square and the square root cancel out. So I got 23/17 multiplied by 1, 4. So the meaning of this answer, this would be our orthogonal projection W of U on L. So if we think about this really, if I'm rounding it, it's about 1.35. I'm just going to go to about 2 places. and then 5.41. So and that's on the red line. So if I go and I graph that, so 1 would be over here, so it's a little bit more than that, and then at about 5.5 or so, almost right where I drew my arrow. So that's kind of, where I'm looking at. I want to try to come up with a perpendicular from the red back to the blue. My drawing's not the greatest, but that's our goal. So this kind of gives us a location. So now to find the distance, we calculate the norm of vector u minus vector w, which was our approximation from before. So this would be the norm of 3/5 minus 23/17. Can't get worse than this, by vector 1/4. So just a bunch of messy arithmetic. This equals the norm of 3/5. Not 3/5. 3/5. It's not a fraction inside. Bad habit. So it's 3/5 minus 23/17 as your first component, and then 92/17 as your second component. So then using common denominators, 3 minus 23/17, you want to convert the 3 to 51/17 so that you have common denominators. 51/17 minus 23/17 is 28/17. And then on the bottom, you would then have this as, we also need over 17. So this would be 85/17 minus 92/17. That's -7/17. So that's what our difference turns out to be. And to finish it, to find the norm, I'll go back up here since I'm running out of space. To find the norm, I'm going to square each component and then take the square root. So I would be squaring 28/17 and -7/17. So after you get through all that, it should work out to 7^17/17. The fractions add up together to 833, which has a perfect square inside of it. So it allows you to simplify it out a little bit to a final answer of 7^17/17. So that'd be the distance between these two, and it's pretty close. Radical 17 is a little bit more than 4, so we have here a little bit more than 28/17. So the distance is between 1 and 2, which is what our picture suggests as well. We're starting a little bit more than 1 and going a little over 2. So I think that matches up with the graph's intuition. All right, we did the heavy lifting on the last part. 2 quick other properties of vectors. I'm choosing to go over these because they do show up in advanced math. For those of you who are in real analysis or are taking it at some point, you will need to know the Cauchy-Schwarz and triangle inequalities. So the triangle inequality might already be familiar to you from high school geometry. In high school geometry, you learn that if you have any 2 side lengths in a triangle, their sum must be greater than the third, or else you can't have a triangle. So if I had like a side of 8 and a side of 5, I can't have a third side of 14. It would not fit. Even if I laid them flat out next to each other and not bending at an angle, they would never be able to cover 14. So generally speaking, any 2 sides add up to more than the third. And with vectors, we can do the same thing. We can say that the norm of u plus v is less than or equal to the norm of u plus the norm of v. And this can be best seen through drawing a parallelogram. You can kind of check it out here if you're interested. So that is also labeled Theorem 6.4 in your textbook. And this works for any vectors in Rn. There's also the Cauchy-Schwarz inequality. Cauchy was a very popular mathematician in the 1800s. Lots of work in real analysis and sequences and all sorts of branches of math. Brilliant mathematician. And what he determined was that if you find the absolute value of the dot product of two vectors u and v and Rn, that will be less than or equal to the product of their norms. We're going to go through two quick examples to show that both of these results do hold up if we try them out with vectors. So first, we will illustrate the triangle inequality. This states that the norm of u plus v is less than or equal to the norm of u plus the norm of v. So to do this, we will calculate individual norms first and then calculate the norm of the sum. So for the norm of u, that would equal 2 squared plus negative 1 squared plus 3 squared. So I have 4, 1, and 9. That adds up to 14. So the norm of u is 14. The norm of v is 4 squared plus 0 squared plus 1 squared. That's radical 17. For the norm of u plus v, these should have things over them too. So for the norm of u plus v, I think it's best to first add them together before we go ahead and do the math. So if I want to just write out a vector that contains the sum, simply add up component by component. So 2 plus 4 is 6, negative 1 plus 0 is negative 1, 3 plus 1 is 4. So if I then turn around and find the norm, I would have the square root of 6 squared plus negative 1 squared plus 4 squared. And that equals 36 plus 1 plus 16, or the square root of 53. So now that I have my results, I want to go back and see, does this actually hold up? Is radical 53 less than or equal to radical 14 plus radical 17? So using a little bit of mental math, we know that this is, a little bit more than 7. So just keep that in the back of your head. This is a little bit more than 3, kind of close to 4. And this is a little bit over 4. We can check because it seems to be very close. So I'm going to grab my calculator just to have some concrete calculation here to make sure that this does hold since it's so close. Radical 53 is 7.28. Again, approximate. Radical 14 is 3.74. And then radical 17 is 4.12. So definitely the right side is bigger than the left. So not surprisingly, the triangle inequality does hold. And for our last example, we're going to take a look at illustrating the Cauchy-Schwarz inequality. So here we want to show that the dot product of the two is less than the product of the norms. So first, let's calculate the dot product of the two. So that would be 4 times 2 plus 2 times negative 1 plus 1 times negative 1, which is 8 minus 2 minus 1, or 5. So that's 1. Next, the norm of u, that is the square root of 4 squared plus 2 squared plus 1 squared. So I have 16, and 4 is 20, plus 1 is radical 21. And then the norm of v, that is 2 squared plus negative 1 squared plus negative 1 squared, which gives us radical 6. So now we want to see if the Cauchy-Schwarz inequality holds up. So is it true that the dot product of u and v is less than or equal to the norm of u times the norm of, so bad with these, I did this on the last slide too, the norm of u times the norm of v? Big question. So I have absolute value of 5, that's just 5, and then I have radical 21 times radical 6. And this one I think we can do via mental math. If I do multiply these together, is 5 less than or equal to radical 126? And the answer certainly is yes. So these two vectors do follow the Cauchy-Schwarz inequality like they're supposed to. So these aren't even really a yes or no question. This is just show that it works. This is a property of vectors. All right, so this was a tour of the geometry of vectors. Be sure to read your textbook section 6.1 for an additional set of examples that are different from these. And I look forward to discussing this more in class with you this week.